Questions first. The first question is, I saw experiment 2. There's still confusion about experiment 2. Experiment 2 is not just the graphs. A lot of people just want to turn in the graphs alone. You also have to do the calculations. Now, if you look at the calculations, I gave you the equations for those, so you just plug in the numbers and crunch it. And then there are a couple of other calculations. Hess's law, you just add it up. And then a percent difference calculation. And so the report shouldn't take more than 20 minutes, 15 minutes, I think, to complete. I don't know, how long? Did anybody finish it?
I'm halfway, but I'm studying for the test.
Okay. Yeah, so just finish up those calculations. You already did one of them, the calorimetry calculation. The other 3 are just like it. How long did the calorimetry calculation take? No, not long. You know, it's not a hard report to complete. And so, yeah, turn that in. Let's say next week. How about that?
After the test?
After the test. Yeah, Tuesday or something.
Tuesday.
Tuesday next week.
Okay, that's good.
All right.
And then we can, that would be good for...
Yeah, that's good actually for reviewing for the final, the calculations, you know. It'd be a calorimetry calculation for the final. All right, the other question is about benzene. You know, benzene, all the carbons are sp2. And so if you were to show the bonding network, we could show it, you know, if these are sp2, we're going to have 3 sp2. You know. And so the sigma bonding network is going to be something like this. You know, where we got the sp2 sigma bonds here. And the pi bonding network, all the carbons are the same. The pi bonding network is like this, where the p orbitals. Yeah. So you have it where you have it localized like this, you know, double bond here, double bond here, double bond here, single bond, single bond, single bond. Or, you know, in benzene we know when we have these, we can delocalize the pi electrons over the entire ring, like that, because all the p orbitals are lined up with each other. And in fact, that's what we see. The electrons are totally delocalized. That adds additional stability to these. And so they have a class of compound. The class of organic compounds where it's delocalized like this, those are called aromatics. You don't have to remember that name. But,
so that's what we have to know for that section?
Yeah. Well, no, this is just valence bond, you know, drawing the orbitals, that kind of stuff. You probably aren't going to have benzene, but, you know, benzene should be pretty straightforward to draw out, nonetheless, you know, because it's all sp2. That's for valence bond. For MO, it's a bit more complicated. MO, you don't have to do that. Now, MO, you have to do diatomics, though. And so what was it? What were the diatomics in number 30?
Okay, so we have CO.
CO.
CN.
All right, let's just do CO first. Carbon monoxide. Carbon monoxide, you should be able to do this using valence bond and molecular orbital. And so for valence bond analysis, let's just do that first. For valence bond, if we take a look at this, we have carbon, we got an oxygen, we need a triple bond here. This Lewis structure is very unusual. Why is this Lewis structure very unusual? Because carbon has and oxygen has a what? A triple bond is nothing unusual. Well, from an octet perspective, nothing's unusual. Both atoms have an octet. What's unusual? What do you do when you look at or analyze Lewis structures? Formal charges. What's
so 1, 2, 3, 4, 5, 11. So it would be
minus one for which?
For carbon.
Carbon. Oxygen is plus 1. This is very unusual. Why is this very unusual? This is extremely unusual, and because
Oh, because oxygen's electronegative, so we should be getting more of the
Oxygen
It's more electronegative than
Yeah,
carbon.
oxygen is more electronegative than
So
carbon.
we expect a higher.
So you expect what?
to pull electrons.
To pull more electrons.
Yeah.
To have a higher density of electrons.
Well, look at the charge and tell me based on the charge what.
Oxygen's more like carbon pull.
What do you see when you look at the charge? What's the story? You can tell me.
Carbon.
Carbon is a stronger attractor.
Yeah.
Not that carbon's a stronger attractor. The story is that
That is pulling more.
not pulling more. Let's just say carbon.
It's more electronegative.
Look at the charge and tell me. When you see a plus charge, what does that mean? If you see a plus charge, it means it lost an electron. If you see a negative charge, it means it gained an electron. So plus charge means it lost. Who lost the electron? Oxygen lost it too.
Which is unlikely.
Carbon. Does that make sense? No, it doesn't make sense because oxygen is more electronegative. Oxygen is stronger. So how come?
How is the carbon able to get?
Yeah, how is that so? Can you come up with a reasoning for that or some kind of explanation?
Isn't that exception?
It's not an this is not an exception memorized, but you look at it. This is the only structure that you can come up with an octet for each, and so either we go with less than an octet. If we go with less than an octet, we could get this. What are the formal charges here? 0, 0. We could either go with less than an octet, or we can go with an octet. If we go with less than an octet, then it's okay. 0, 0 is good. But if we need that carbon to get an octet, then carbon has to pretty much take the electrons from oxygen. Is it going to happen? Well, it depends. It depends on, how important is it to have an octet versus not an octet. How important is an octet?
It is important.
Unstable.
Yeah, it's important, and it turns out it's more important. It must be more important than this. So, I guess I didn't unlock that one there. The situation here is this. Which one depends on, experimental evidence. Experimental evidence suggests that this is the correct structure. So, based on experimental evidence, it tells us that what's more important?
The octet.
Having the octet. Having the octet, except for, this is the exception you need to memorize. Except for fluorine. What's more important here? Having the 0 formal charges like this and no octet, or fluorine giving up electron, boron.
Having the 0. Because fluorine doesn't.
What are the formal charges that result when we get an octet here?
It'll be -1 on fluorine. And the 1.
Oops, no, sorry. This is it now. What are the formal charges here? +1 on fluorine and so on. So what's the story that this one tells?
Fluorine is not going to give up.
The fluorine gave up an electron to boron.
It would not do
It would not do that. And so this is why there's the two-pronged. Remember I talked about this two-pronged approach? Somebody explain what the two-pronged approach is. Theoretically. So theory is octet rule, formal charges, all that stuff, right? And just based on those rules that we need a little bit more. We need some factual knowledge, some memorized knowledge. This is the factual knowledge. Let's see. In this case, we get an octet, but we have weird formal charge. In this case, we don't have an octet, but we have good formal charges. Good meaning nobody has to lose, nobody has to gain. And so the thing that you memorize is that hydrogen and chlorine only form one bond. Oxygen here, well, it happened, you know, and this changes the reactivity of carbon monoxide. Carbon monoxide is very similar to something else, you know, cyanide. Carbon monoxide and cyanide have very similar Lewis structures. They both have a negative charge on carbon. And they both have similar chemical properties. One of the chemical properties of these two, these are powerful Lewis bases. They're strong Lewis bases. They're strong Lewis bases because of the negative charge on the carbon. So this attacks things like hemoglobin. Hemoglobin is the Lewis acid. So cyanide and carbon monoxide do the same thing. They bind to hemoglobin in your blood and prevent oxygen from attaching or binding. And so, well, anyway, if we do this, then we could do the valence bond analysis for this. Are you guys okay with the valence bond, or do you want to do another example of that, or what? Maybe I better. So let's do the valence bond for carbon monoxide. What's the hybridization on carbon?
SP.
And oxygen?
SP as well.
SP. And so you guys know how to draw the orbitals?
It's going to be
Yeah.
one be like this, the other one like
At what angle from each other?
this. That's going to be like this. And then the P coming up
Okay, the P coming up.
and down. That's just one.
Okay, up and down is one.
Up and down and then going in to the border.
Okay.
In the middle.
All right.
That'll be another P.
Be another P here. Is there another P? Okay.
That's what you have.
All right, so I have these four orbitals.
You have
Right, I have the two sp orbitals, sp, and the two p orbitals. How do I fill them?
you have lone pairs, so you have to do
Lone pair in which one?
in the SP,
This one?
and then electrons in the rest. Just
Yeah, how many electrons does carbon have? 4?
3.
1, 2, 3, 4? Is that right?
No, you have one more.
I have 5 because... Hmm? Yes. With a negative charge, I got 5. And so we'll put them in 1, 2, 3, 4, 5. That's 5 of them. And then oxygen,
It'll be SP as well. So it's gonna
would be sp. So I'll draw sp, sp,
And the P going up and down.
p going in the plane,
And the one coming.
one coming out. So oxygen has 4 orbitals, 2 sps, and 2 ps. Okay, how do I fill them?
So the lone pairs in the SP on the other side.
And how many electrons does oxygen have? 6?
5.
Oops. You know what? I need to go spin down.
Yeah. faster?
Yeah.
This is just like a minor thing, but just to make sure. If I write SP under the 2 lines and then P under the 2 lines, would that matter? Or would I have
That's
to-
okay.
That's okay.
Yeah, you don't have to label them individually. You do have to label the orbitals.
Yes. And the bonds, right?
Yeah. So we have what? We have a SP sigma bond, right?
SP, yes.
We have a
PP pi bond.
PP pi bond, and we have another
PP pi bond.
PP pi bond. That gives us our triple bond. Is this diamagnetic or paramagnetic?
Paramagnetic. No, diamond.
It's diamagnetic. All the electrons are paired.
Oh,
So diamagnetic. It's got a triple bond. The bond order is 3. Okay. Erase this.
and that would have to agree with the molecular orbital, right?
No.
Can that disagree? Because
Yeah.
when we did oxygen,
Right. Oxygen
it
disagreed.
fell, so
Doesn't have to agree.
it
Let's
doesn't
see.
have to.
How did you know that's the diamagnetic?
We have no unpaired electrons. All the electrons are paired.
You think about
This one is paired with this one.
Oh,
This
okay.
one's paired with this one. This one's paired with this one. This is a lone pair. That's a lone pair. Everything's paired up. All right. Oops. I forgot one thing.
It's just
You could have done it like this, you know, if you want to. That's fine for carbon.
yeah, so that's usually what I do.
Yeah. And then this, is this what you do? You do oxygen SP, oxygen P,
No, it's the same
oxygen P.
It's the same
No,
oxygen.
yeah, you don't want to do that.
Can we just write oxygen in this?
Yeah, you would write oxygen,
And then,
then SP, P, P.
oh wait, do we have to write that?
What?
SPPP?
Yeah. This is SP sigma bond, PP pi bond, PP pi bond.
Oh, okay. So we have to write.
You should, yeah. Tell me what orbital.
Oh, because
the
before I
electron
would just
comes.
write the oxygen.
This
and
is,
Charlie.
no. No, you need to tell me.
I need to tell you. Oh.
Yeah, don't leave it like this.
Oh.
Okay, yeah, I want you to tell me it's an SP electron from oxygen going to an SP electron, carbon.
Oh, okay.
Wait, so do we do the same with like oxygen's own orbital?
Yeah,
Okay,
you do the exact same thing with oxygen. You know what oxygen would look like?
the same thing,
Yeah.
except
Except this spins.
It's so like precise. You have to like look for it. Span.
All right, that's a valence bond. Let's take a look at MO now.
Yes, that's what I have there.
MO, which diagram are we going to use? Z less than 8 or Z equal to greater than 8?
Well, carbon is less than 8. But
Yeah, less than 8. Even though it's carbon is less than 8, oxygen is equal to 8. And so we have a conflict. But based on what we saw earlier, we'll use carbons. Just use carbon.
So how do we choose? How do we determine? Like, because
That's it. If you have a heteronuclear, this is all we can do. Based on what you've seen, if we have a heteronuclear, just use carbon. I mean, use the one that's lower.
so always the one that's
If you have homonuclear, then
it's different.
yeah, and so you have 3 choices. Homonuclear, less than 8, homonuclear, greater than 8, or hetero. Hetero, use less than
Less than 7.
8. That's it. You only have 3 choices.
7.
And so we will use carbons, right? And this is just to make things not so complicated. If you want to, you know, if you want to be very precise and accurate, then you'd look it up because it depends on how the energies change, the repulsions change.
So there are 3 boxes going on.
Yeah, you got the sigma 1s, sigma star 1s, and then for carbon, do you have the repulsion or no repulsion? You have the repulsions, right? And so you have the pi's, followed by the sigma. This is weird because the sigma 2p should be lower, followed by the pi stars. followed by the sigma star. Right?
It's less than 7.
Yeah, less than 7. The carbon monoxide has how many? There's 4 valence electrons and 6. So that gives us 10 electrons. Valence. This is valence because, I'm sorry, this is 2s.
Yes.
Because we don't care about the core right now. We aren't going to show it. The core are there, but we're just doing the valence. All right, next, it's 10 electrons, so 1, 2, 3, 4, 5, 6, 100, 7, 8, 9, 10.
So is that?
So it's diamagnetic. What's the bond order? Well, these cancel, so that's triple bond, right? Bond order 3. It was a triple bond. And so when we look at carbon monoxide, we got the sigma 2s electron density here. Then we have the sigma star 2s, which is antibonding. We color that red. Antibonding, sigma star 2s. And then we have the pi 2p's. Well, there's going to be a pi 2p up here, one lobe, and down here. That's one of the pi 2p's. Where's the other pi 2p? Well, it's one's coming out, and the other's going in, the 2 lobes. Okay. So this is the other pi 2p. So here's one pi 2p, here's the other pi 2p. Just sticking out. And then we have a sigma 2p. This is sigma 2p's looking like. Sigma 2p's looking like this. So we map out the electron density, it kind of looks like that, which is similar to the valence bond, you know. But the valence bond has this lone pair sticking out over here, a lone pair sticking out over here. But it's quite similar, and there's electron cloud coming out here from the sigma 2s. It's different, though. Do you see it's a little different? Okay.
Do we have to draw that?
You don't have to draw that. I'm just showing it. You aren't going to have to draw that.
If the bond order is 0, it means that it's not stable.
Right.
This
If a
means
bond
that
order is
otherwise
0, it's not going to exist.
it's not gonna
Yeah.
exist.
There's no bond.
And if it's like
What
a
if-
fraction, well, what does that mean?
If it's a fraction,
It's still stable, but what
yeah,
is that?
yeah. Like
It's-
1.5 bond means it's stronger than a single, but weaker than a double. That's it.
But does it exist then?
It does.
Yeah.
Let's say I ionize this. I take 1 electron out.
It's carbon.
Then what's the bond order? 2.5. 2.5 is stronger than a double, but weaker than triple. If I ionize another electron, bond order goes down to 2. All right. Are we okay with this? Basically, you do this part,
The what?
the diagram.
The diagram, but we didn't do that.
You don't have to do that part.
So we
All right.
use the lower than 7 diagram for
Yeah.
for this.
Heteronuclear, just use the lower than 7. Just be consistent. Make your life easy. All right, other questions?
That's insane.
All right, no other questions? Okay, all right. Let's analyze some more acids. You know, to compare. Let's compare H2SO4 versus H2SO3. Well, first thing is we have to draw out the Lewis structure for H2SO4. So go ahead and draw out the Lewis structure for this. This is I'm going to finish up chapter 16 now.
That'll be the last chapter, right?
No,
No.
no, we have more.
We're turning more homework set for the final.
Yeah, your last homework stuff will be due on the final.
What will be the chapters?
Hmm?
What will be the chapters for homework?
11 and 12.
Two chapters for the final.
Hmm?
Are we turning for final? Two chapters for homework?
He's asking for the final with chapters.
11 and 12. Chapters 11 and 12.
For the homework.
No, we
right?
did 11.
Oh, did you, I mean 12 and 13. 12, 13, and 16 is the homework stuff.
Which one was it? 12.
Just the whatever's left over, that's what we're going to turn
12,
in.
13, and 16. So we have 3 chapters before the final.
Yeah. Well, no, 16 we're finishing right now. This is it.
Yeah, we're studying for the test.
I know.
Two chapters for homework.
Uh-huh.
Three chapters?
I know. No, yeah, that's why, 12 and 13 aren't going to be in-depth coverage.
Okay.
13 is there, I don't know if you caught this, yesterday I was talking about this, but maybe it was the afternoon class. Yeah, 13, there's only a couple of things of importance in that. 12 has more, 12 has 3 or 4 things that are important, but
And the final will still be everything, right?
finals everything, right? And so the depth that I cover the remaining stuff isn't that deep. Like 13, you should just be able to do based off notes alone,
So emphasize on the notes rather than.
Well, that's all that I always say, but some people.
But like homework wise?
But if you're going to do based on the book, then forget it. You're going to have a hard time.
I'm saying for the homework because like some of the homework problems.
Yeah, the homework is very short. Did I post 13? No, I need to post that. It's a very short homework assignment. So did you guys have H2SO4? The Lewis structure, what did you get? Sulfur in the middle? And what else? Sulfur, and then where are the oxygens? Did you get a hydrogen bonded to the sulfur?
No, it has to be bonded to the oxygen because it's an acid, so it bounces more electron.
Yes. Did you guys catch that? There are no hydrogens bonded to the sulfur. It's an acid.
It's an acid.
The hydrogens are going to be bonded to the
More
most
electron.
electronegative. So something like this?
Yeah.
Then you completed the octets?
Does it matter where you put the H,
It does not matter because what is the shape of this? Tetrahedral. Tetrahedral, is there top, bottom, side, right side, left side?
Cylindrical.
It's cylindrical. It's what we call spherical symmetry. They're all the same. If you just write it on paper, it matters, but in reality,
Space is
it's spherically symmetric.
So for the test, you said we didn't have to memorize, like, well, I didn't know what you said. You know how there's like a chart, like in the book?
You don't have to memorize what?
You know how there's a chart in the
Yeah,
book?
yeah.
So do we have to memorize all that?
What do you mean memorize? The shapes?
Yeah.
I don't think I ever said you don't have to memorize the shapes. You have to know the shapes. All of them, yeah. You need to know them.
like a geometry?
Yeah, this is tetrahedral. All the positions are adjacent, and so if I put them here, it's the exact same thing. The angle here is 109, angle here is 109. It looks like it's a 180, but it's not. And this is not a 90. And so it doesn't matter which ones. But is this structure okay? Well, there's something funny about this particular structure, and that is this is negative, and this is 2 plus. And so this is kind of a high formal charge. And so we have different options here. Option 1, okay, this is structure, we'll call this structure A. And let's go to structure B. Structure B is if we expand the octet by 1.
Yeah, we can do it. Sulfur is okay.
What this does is it knocks down the formal charge by 1. And so we go here, this is a,
Wait, sulfur?
yeah, +1, this is a minus. And so which one looks better?
B.
Yeah, B looks better, right? And then we could draw a resonance structure for this. What would the resonance structure be? And then the resonance hybrid?
One permanent bond and then
Yeah.
half and then the located.
Right.
What about geolocated?
Um, yeah, it is.
Right, delocalized. Okay, but you know what we can also do? Is it okay to expand the octet on sulfur?
Yeah.
How come?
Also an exception.
Isn't it the size of it?
It has a d orbital that's accessible, right? But there's one issue with this, you know, and that is this. Here, I want to leave this up here. Okay, I'm going to erase structure A. And what is the hybridization on sulfur?
SP3.
sp3. And so sulfur is sp3 hybridized. Let's put this sp3 orbital coming up here. There's 3 more sp3s, but let's focus on the sulfur-oxygen bond. What's the hybridization on oxygen?
SP2.
sp2. And then the lone pair here, lone pair here. Now let's do the top view. So where's the p orbital on oxygen?
It's like coming out.
Coming out. This is the p orbital, right? Where's the p orbital on sulfur? It doesn't have a p orbital.
What? Why
Sulfur
is it
does not have a
sulfur?
p orbital.
Wait, so what? How would it?
Because when we look at the energy level diagram for sulfur, let me rotate the camera back. When we look at the energy level diagram for sulfur, we have our 4 sp3 orbitals. And then we've ran out of p orbitals.
Wait, so what do we do?
Well, how many electrons does sulfur have in this particular structure? Count them.
5?
5. 1, 2, 3, 4. Now the 5th one, should I pair it? No, where do I put the 5th one?
In a D.
It has to go into a D.
Ah.
5th one goes into a D.
Oh, that's gonna be tricky. Wait, do we know the shape?
Do you know the shape of a d orbital? What does a d orbital look like?
I don't know.
Okay, I'm going to do 2. Looks like a what? It looks like a earlobe. I don't know what a earlobe looks like. I mean, you know, the d orbital should be like.
All
Wait,
your
did we
looks are
learn that?
different.
Are we just learning about these now?
D orbitals? You don't remember what d orbitals look like? I called it. What did I call it? I didn't call it earlobe. I called it a 4-leaf clover.
What? Was I here?
I'm pretty sure you were here.
Yes.
Today, first time.
You don't remember? I don't remember it. You remember it? Was that the afternoon class?
No, I showed it on the projector.
This one, I got it.
It's from chapter whatever. What was that chapter? The quantum chapter, chapter 8. This is
Yeah,
chapter
they
8.
should,
You don't remember? We talked about the s orbital, the p orbital,
I got it.
and then there's a homework problem, which we talked about. The homework problem showed a d orbital, but it had some nodes,
So in the test,
an additional nodes. Do you remember that?
No.
The homework problem? Seriously, you don't remember that homework? I thought it would be
That's why I got
memorable
really good
because you'd go,
I got-
what
I
the
got the
heck is that
question wrong.
orbital?
I got the question wrong.
In the test, you asked the four leaf, and I'm like, what?
The four-leaf clover? Oh.
I was like,
Yeah.
what is he talking about?
Never heard of it.
Oh, okay.
That's why I was like,
that's-
false. It might be false if I don't know about it.
All right, this is one orbital. It has altogether how many lobes? 4 lobes. So this is a D here. And let's look at the p orbital side view. So if we look at a p orbital side view, looks like this, right? And let's bring the d orbital and the p orbital together so they overlap. So it's going to look like this. So what do we call this bond? Let's draw the internuclear axis.
Wait, would that be sigma? Oh yeah, I guess it's
What's the difference between a sigma and a pi bond?
the sigma is along the axis,
Parallel or forward.
and the pi is like parallel to the axis.
No,
It's the opposite.
no, that's not how they're defined. It has to do with the internuclear axis. Does somebody remember?
The electron cloud of the sigma bond is bounded.
Yes.
That's what I said. That's what I
No,
said.
it's in
In the pi bond, the overlap is above and below the internuclear axis. In a sigma bond, the overlap is along the internuclear axis. You remember that?
wait, so,
So what kind of bond is this? Is it a pi bond or a sigma bond?
It'd be a pi bond.
This is a pi bond.
Yeah, it's a pi bond. It's not along
okay.
Can you say-
This is called a dp pi bond.
Why is it? Why
the
is it
professor.
pi?
For the test, it's Thursday. Do we have to know how to draw
No,
SP3D?
SP3D? You don't know how to draw SP3D?
I'm just learning this right
There's both ways.
This one? This is not SP3D.
The D orbital.
This is SP3 with unhybridized D. When you say SP3D,
now. Oh, that I mean.
I'm thinking trigonal bipyramidal. SP3D, 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 then one SP3D coming out and one SP3D going in. This is SP3
With an
and
hybridized.
D. And D. This is SP3D. This is SP3 and a D orbital. One of the 5 D orbitals. This is SP3D all hybridized and mixed together. Does that make sense? And so this is unhybridized. Unhybridized D. Unhybridized D orbital.
Do we have to know?
This is a D orbital that's hybridized. No, why do you think I separated this from the rest of the chapter? The reason I separated this from the rest of the chapter was not to overwhelm you guys. You know, this is more advanced stuff in chapter 11, so I thought I'll put it off, you know, until later. And so this is why I didn't talk about it during our talk about. Does that? You probably a lot of people have already read it. So I was talking to people about this yesterday. I told them to wait until today when
This book is.
I plan to talk about it.
What
And
was it?
so-
I don't know.
So,
Really.
so then we're responsible.
This is the
obviously, for
advanced stuff. Actually, it's not the advanced stuff. This is the regular stuff. It's just the harder regular stuff. And so what you want to know is at least know the basic stuff, you know? at least know and then if this stuff is too confusing, okay, that's fine. You know, this is a little bit more advanced stuff. But you want to know the stuff that I talked about last week, you know, for sure. Okay, but for those and also this is important because, but the advanced stuff is, you know, for the ones striving for, you know, deeper understanding of this. Okay. But usually when I group this in with all the other stuff, it blows people away. The people who just want the basics, they don't want to go advanced, you know. They just want to do the minimum and get past the class. And so this semester I separated it. Actually, in past semesters I've been separating it for a while.
Can you explain why it was pi bond again?
Why it's a pi bond? Okay. This is a p orbital. This is a p orbital. Is that a sigma bond or is that a pi bond?
Sigma.
How do you know it's a sigma bond? Because what you do is you draw a line called the internuclear axis. All this does is connect the nuclei. And then you focus on where it overlaps. And then you look, is the overlap within the internuclear axis or outside the internuclear axis? It's within. And so we call this a sigma. Anything where the overlap is within the internuclear axis, we call it a sigma bond. Versus a pi bond. I mean, you could visualize a pi bond and then just do the same thing. Here's a P. Okay. Let's try to draw this. P, sigma or pi. So draw the internuclear axis. Do we have overlap within the internuclear axis? No, we have overlap outside the internuclear axis. Therefore, it's a pi bond. Pi bonds, are they stronger or are they weaker?
Weaker.
They're weaker. Why? Because what's pulling the two nuclei together? The negative charge density. Negative, 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 negative. The two nuclei are being pulled towards straight to each other. Whereas here, are the two nuclei being pulled straight to? No, they're being pulled up and down, and the net is they're being pulled towards each other. Right? But the electron cloud's not concentrated here. There's only 2 electrons worth of density here. But we got all 2 electrons worth of density concentrated here, so sigmas are better than pi. This is why a sigma MO should be better than a pi MO. And so this is why a sigma 2s should be lower in energy than a pi 2p. But it's unusual that it got bumped up in the z less than 8. It's unusual it gets bumped up because this should be a stronger, more stable, lower energy orbital. So that's what I did here. I just looked. The overlap is here, and the overlap is here. Is the overlap within the internuclear axis or outside the internuclear axis? Outside. So it's got to be a
DP bond, pi bond.
pi bond. DP pi bond. What would the top view of this look like? The top view would look like this. This would be a DP pi bond. Do you see it? Can you see it? And so let's go back to this. we need to do oxygen. Oxygen is going to come in here with an sp2 and sigma bond with sulfur. And then it's going to come here with a p and pi bond. This is going to be p, pd pi bond. And so the d orbital is going to stick out. D orbitals are big. One's going to stick out like this. I mean the lobe. And one lobe sticks in. There's 4 lobes. So this would be the side view of the PD pi bond. Well, not side view, top view. And then we could tilt this to the side. If we tilt this to the side, we're going to get this.
So we have
Do you see that? PD? No, not at all. You know, don't expect a lot of this stuff. You have to go back and review if you don't see it right on. But basically, we have 1 electron in the D. And 1 electron in the P. This creates our PD pi bond. Yeah. PD pi bond. Okay, the next thing that we'll look at is decreasing the formal charge a little bit more. And so this is an unusual bond. Tell me about this bond here. It's a sp2, sp3, sigma, and a PD pi. We could also lower the formal charge a little bit more. If we lower the formal charge a little bit more, we could do this. So we lower it. What are the formal charges here? Everything's 0. This is great, you know. Formal charges are down. Except one thing. You know, this is an sp2 sigma, but this is a, what is this? Let's take a look. So sulfur is sp3 hybridized. And how many electrons does sulfur have? 6. 1, 2, 3, 4. Where should my 5th electron go? Into the D. Where should my 6th electron go? Also into the D. And so what this means is this. This means I have a PD pi bond here. And I must have another PD pi bond here. And so one of the oxygens comes in. An oxygen sp2 comes in, bonds here, and a P bonds here. So that's 1 PD pi bond. The next oxygen comes in, and we got an sp2 coming in here, and a P coming in over here. So we have two PD pi bonds. Do you guys remember the? I showed this I don't want to turn on the computer just right now, but I showed the d orbitals, and they're in the planes. You know, we had the dxy in the xy plane. You guys remember that? Some of you? Anybody? Remember this? Yeah? Or not at all? You know? Okay. And then where are the other d orbitals? In the xz and in the yz. And if we think about these planes are like this, and like this. The planes are at what angles? At 90-degree angles. What's the angle here? About 109. And so, you know, is that second pd pi bond, you know, let's say the d orbital's here, right? Is the second pd, the next d orbital should be at a 90 angle, but this is at a 109. And so, do you think that next one is going to have good orbital overlap? Are the orbitals lined up right? No. And so having multiple pp pi bonds is no problem, because you know the p orbitals are 90 and we're okay. We just saw that with a triple bond, right? No problem there. But I think you can assume that, you know, maybe having two pd pi bonds is going to lead to some stress, you know. And so let's talk about the bond. Let me talk about this. Let's say this is a p orbital here. This is a p orbital here. Good overlap. This is atom A. This is atom B. This bond looks like this. It has a kink here. So rather than just drawing a straight line to B, we draw a kink line to show it's kink. The bond is kink. Kink bond's good? No, because the overlap is projecting out this way, and this one's projecting up this way, and we aren't going to get great overlap here. This is going to be a weak bond, right? Stress, because the bond angles, or the angle is funny between the atoms. Does that make sense? And so we don't draw a kink. And so if one d orbital is pointed this way, the other d orbital is pointed this way, it doesn't quite line up with the geometry, and probably aren't going to get such great orbital overlap. And so here, the second pd pi bond might be strained. Now, there are things that can happen, like hybridization. Maybe there's less D character. You know, maybe we do some hybridization here and do this. And so the end result is this. Forming one pd pi bond is, people usually do that. That's okay. But forming two pd pi bonds, we have to do a second thought on that. Does that make sense? We could have a pp pi bond and then a pd pi bond. That would be okay. But let's take a look at another example here.
Wait, well, we didn't finish the sulfuric versus sulfuric.
Yeah, we're gonna finish that. So what it boils down to is this: the best structure based on recent calculations. Let's take a look at PCl5 again. Do you have a chance to review this one for the test? Yes? Okay. We said that this one is going to be what hybridization?
That's gonna be on S.
sp3d. Hybrid. And we get these 5 orbitals that have this shape, right? But
It's octahedral. No, that's
trigonal bipyramidal. And so best structure based on recent quantum mechanical calcs suggests this. There are only 4 bonds.
What about the fifth one?
The 5th one, well, if there are only 4 bonds, what's the formal charge on phosphorus? Plus 1. The 5th one is an ionic bond. Like this. And so basically, phosphorus never goes beyond an octet. And if there are more, then the extra are held on by ionic bonding. So this is ionic. Really, though, how many resonance forms can we draw for this?
1, 2, 3, 5. 4 bonds.
We can draw 5 resonance forms, right?
For each chlorine.
Right.
Wait, that's
Plus 4 other resonance forms.
How recent is that?
Very recent. The reason why they were thinking about rethinking this whole hybridization business, this is why I didn't spend too much time on sp3d and sp3d2.
Yeah.
The reason they're thinking of rethinking this is because the recent calculations suggest there isn't much d orbital participation. And since there isn't much d orbital participation, then it's got to be something like this,
So it's like
where we utilize just the valence, I mean the whatever, not the valence, yeah, the valence, the S and the P here.
Is it likely to change? The whole
Well, when we
explanation
do this, neither of these is correct, actually, because when we have these resonance forms, then what's the best structure? The hybrid. And so the hybrid is like this. You know, the hybrid, there's going to be what kind of charge on each chlorine?
No, it's gonna be
I'll just draw the hybrid like this.
1/5. Negative 1/5.
Yes. Yes. Each chlorine is going to have a negative
1/5.
1/5. Oh, just to, you know, because I know this stuff is probably like, whoa, you know, it's too much. But you got to realize this is like what it's going to be like when you transfer, because each successive course you take is like, whoa, you know. I thought the last course was bad enough. Now I got something much worse. And then every quarter is like that. Like, okay, that's got to be the hardest. I got to be over the hump, right? But you aren't over the hump because it just keeps getting, seriously, it just keeps getting harder and harder.
Wait, how do you know it's
Is that chemistry?
That's how chemistry is. That's actually how all the majors are, you know? Because it just, you do, but the thing is, you take it, the thing is you take it in steps, right? If you were, let's say you fell behind and you're 5 steps behind, right? Then that's a big jump, right? But if you're not so far behind, then it's just a small step up, small step. Yeah, sure, it gets harder, but it's manageable. So if you had this earlier stuff totally dialed in, you know, sp3d, all that p pi bond, then this is just another step beyond.
So
Sorry, where did the bit conversation?
Well, let's draw another resonance form. Here, the next resonance form is, let's put the chloride up here.
Bring the ion.
Do you see how it's going to be in all 5 positions? And so if you average it, it's going to be negative 1/5. Negative 1/5. Phosphorus is plus. Yeah. And so, do you see what this is? When you look at the hybrid, what it is it's a mixture of covalent and ionic bonding. And so, instead of describing the bonding as covalent or ionic, you know, covalent or ionic is black and white, right? Is it covalent? Is it ionic? Rather than thinking in that way, we can think in terms of percentage ionic character, right? And so what we have here is this is just covalent, you know, polar covalent. Covalent bonds, 5 covalent bonds, right? This has a lot more ionic character because not only do we have the sharing of electrons here, but we have the attraction between the positive charge and the negative charge. That electrostatic attraction is what we call ionic bonding. And the ionic bonding helps hold the atoms together. And so this is a mix of covalent and ionic bonding. Does that make sense? Or not at all?
No, it does, but it's like they're combining two. It sounds.
Yeah, and so in other words, we have a certain percent ionic character. Okay?
This is a part of the test material.
No, so just completely forget it.
No,
Don't bother.
No.
Don't bother.
Not for this test board, it's for different file.
Yeah, you know what? Yeah, it's for the final, but you know, this is. Do you think? Okay, let me tell you another thing.
It's just for you to have.
Our final is going to be a different sort of final. Our final is not for advanced level questions. If I only gave you 4 questions on the final, I'd probably want a challenge, like a challenge problem, you know, something more challenging, like this, right? But our final is a 60-question final. You know, how many questions do you think I'm going to ask? 15 questions out of 60 on this? And why do you think I separated this? I separated this so if you don't know this, it's not going to blow you out and make you fail the course, right? You know, you should still be able to pass this course without having this mastered. This is not what I call critical. You know, this is what I call advanced for the people who want a deeper understanding. So. I mean, it's not that hard, though. Really, it's what is the when we look at this? What are the formal charges here? What are the formal charges here? 0. And so what I'm going to call this is 0% ionic, right? What do you think now? Do you see that we have a single covalent bond plus the charge separation? And that charge there means that there's going to be a ionic electrostatic attraction. And so what happens to the percent ionic character? It went up. And so now this bond is much more ionic than this one here. right? And so this is the percent ionic character shot up, the percent covalent character
Went down.
went down. It's not 100% ionic, you know, because then sulfur, if this were 100% ionic, sulfur would be +6, and all the oxygens would be -1. Make sense?
Oh,
Right. Okay, then we have this structure here. Okay, what's happening with the percent ionic character here?
okay. It's equalizing.
Yeah, the percent ionic character is somewhere in the middle, right? It's between these two. And so this is some, there's both, percent ionic and percent covalent.
Almost the same. Kind of.
Yeah, kind of. I mean, you know, the percent ionic character just shot up a lot. But, I mean, it's not huge. It's -1/2 on each, right? And +1 here.
But it's closer to the extremes.
Yeah. And so where is the real picture? Is the real picture structure A, structure B, or structure C?
None of the three is a combination.
Maybe B.
Yeah, maybe it's a combination, you know, B, C, A, B, C. You know, it's somewhere between here, you know. These are just the ones at the limits that we have here, but it just,
Fluctuate.
well, it's going to find the right energy balance where things are optimized. That is, you know, creating these formal charges costs energy, right? But we get energy in return by ionic bonding, right? And so there's going to be some part where it's going to be optimized, where it's a mix.
It's like the water.
And so this is what your book says. Your book says the real structure is going to be a hybrid, and it's not going to be a 1/3, 1/3, 1/3 mix. It's going to be a weighted hybrid of which one of these is most stable. Probably B is the most stable because of the, you know, this one we have the 2 PD pi bonds, which is going to destabilize it, right? And so we're leaning more towards this, where the bonding isn't all covalent. There is some ionic character to the bonding. Does that make sense? Okay, so the bonding situation for something like sulfate, even though it seems easy, is complicated. And so what should you do? What people do with this is they go to the two extremes. You know, the actual picture is in the middle, you know, between the two extremes. And so you have a choice. You either go to the extreme and go covalent, or, you know, or you maintain an octet. And so these are the two extremes. Expanded octet, minimum formal charge, or maintain the octet, but the formal charge goes up. Your book suggests going with this, because this shows, you know, the ionic character. But the actual picture is going to be somewhere in the middle, right? Between the two extremes. It's like, you know, when we do formal charge assumes 100% covalent bonding. Oxidation state assumes 100% ionic bonding, but the actual bonding is somewhere in between. This is covalent, this is more ionic, and so the actual is probably this.
Wait, why would the book go with that one?
Because this one doesn't show any ionic character. You know?
What's the significance? So what's the
And so the book says, just go ahead and why don't you just maintain the octet, don't expand it, and show it. Because it.
So that you showed there is some ionic and some covalent as well.
Yeah.
Where this means you're saying that it's ionic.
That's a good question.
Mm-hmm.
What's the significance of showing ionic compound?
No, ionic is ionic. Ionic is ionic. Let's see. Like something like lithium fluoride. Lithium fluoride should have pretty much 0 covalent character. You'd expect minimal covalent character.
Yeah.
I hesitate to say 0 because, you know, even in lithium fluoride, there's some covalent. Yeah. And so this gets tricky. For example, PbCl2 is more ionic. PbCl4 is more covalent. And so PbCl2 forms a crystal lattice of ions. PbCl4 forms molecules of PbCl4 because the bonding is so covalent.
Wow.
You see, so this is the take-home point. The take-home point is that, you know, describing the bonding in these, you know, we just look at the extremes and then say, you know, it's somewhere in between. But, you know, sometimes we're closer to one extreme than the other. And so, for example, PbCl4 was more covalent. PbCl2 is more ionic. So we'll just go ionic, we'll go covalent. Make sense?
So we still go by the extremes here, though there might be some point in between there.
So there's a bit of controversy regarding this one. This one is, we have the octet, except the problem with this is that the formal charge, negative, positive here. This one, the formal charge is good, but we expanded the octet, which we can do, right, because there's the d orbitals here. They expanded. Except this one is interesting because this is sp3, therefore this is a sp2, sp3 sigma, and a p d pi bond. Now PD pi bond is one's okay. And so most of the people write this one like this. Not like this. But what some people are saying is, well, the d orbital participation isn't so high, so maybe there's quite a bit of what we call ionic character in the bond. The more ionic character, the less you have to do d. But the real picture is probably somewhere in between. All right, let's take a break and then we'll continue.